Okay, so how do you solve the selection problem? The idea here is to sort of cheat a little bit, so I didn't give you enough information to solve this. You may have thought about it and come up with a solution, but maybe not. We're going to attach some metadata to each node, and the metadata we're going to attach is the size of the node, where size is the number of nodes rooted at that given node. So for example, the size of the node 8 is, well, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 nodes rooted at 8. So the size of the root is always going to be how many nodes do you have in the entire tree. The size of a leaf node is just going to be 1. And the size of a node like 3 here is going to be 1 over here plus 1, 2, 3 over here plus itself. So 3, 4, 5. So how do you compute the size of a given node? What kind of traversal? So you're going to use a traversal for this. What kind of traversal would you use to compute the size of a given node? Well, this is going to use a post-order traversal. And why is that? Well, for a given node, let's take 3 for example, we need to know the size of its left size, the size of its right size, because we're going to compute the size of the current node by taking the size of the left plus the size of the right plus 1 for the current node. So for example, the first node that we'll compute the size of, so we go left, this is a post-order traversal, cannot go left, cannot go right, so that the size of this node is just going to be sort of the size of a null node. So that one's null, the size of this one's null, so those are supposed to be 0, plus 1, so we get a 1 for that one. To compute the size of 3, well, we also need to know the size of the right. And then we finally get to the 4, it has a size of 1. The 7 has a size of 1, which means the 6 is a size 3. The 3 is a size 5. Next, we traverse all the way down to the 13, give it a 1. 14 is 2. The 10 is 3. And then finally, the 9 is the 5 plus the 3 plus 1 for the node 8. So that might look something like this. Here's a post-order traversal that returns the size of the given node. So if the current node is not none or null, then you say I want the size of the left side, the size of the right side, and then I want to calculate the size of the current node as the size of the left plus the size of the right plus 1. Otherwise, I just return 0. And this pseudocode's a little sloppy in that obviously if I return something here, I should have returned something from the other case. The reason I've done this is I just wanted to more clearly denote that this was a post-order traversal, which is a little harder to see if I would have embedded those lines of code in here and properly wrote that they have to be computed before the current node. Okay, so let's get back to the selection problem. With our new size of each node, here's an algorithm for getting the ith order statistic. And I'd like you to pause this and just read through this code for a few moments. Okay, so let's step through this with an example. For example, let's say we're going to look for the, I don't know, the 4th order statistic. Which would be the 4th biggest number, so 1 is the smallest, so that's 1, 2, 3, 4. So we're looking for the number 6. Let's see how this algorithm gives us that answer. It should give us the 6. So our left child size, we're gonna start at the root. So the current node is the root node. And we're looking for the 4th order statistic, so I is 4. The size of the left child is 5. So we're going to compare left child size to I minus 1. So we're going to say 5 and compare that to 4 minus 1. And they're not equal. And in fact, 5 is greater than or equal to I. So we're going to call get ith order statistic on the left node. So at this point, we've moved from 8 down to 5. So we're at the node 3. So we're at the node 3, and we're still looking for the 4th biggest number. What's the size of the left child? The left child is now of size 1. So we have 1 here, and we're going to compare that to I minus 1, which is still 4 minus 1, which is 3. 1 is not equal to 3. 1 is also not greater than or equal to 3. So we're going to come down here to the else branch. The else branch has us do something kind of interesting. So we have to compute a new value for I. So we're going to say new I is equal to I, which is 4, minus the size of the left subtree, which is 1, minus 1, which is going to be 2. So now we're going to recursively call get ith order statistic on the right node with a value of 2. So we're now here at the 6. That was the right node, and now I is equal to 2. So what's the size of the left child? That's 1. I is 2 minus 1 is equal to 1. 1 is equal to 1, and we've returned the correct value. So this works on this example, but why does it work in general? And in fact, the most interesting part here is why do we have to compute a new value for I when we go to the right? Well, the interesting thing here is that if we were to go to the right, so we went to the right from our node 3. If we were to go to the right and not subtract I, we'd still be looking for the 4th order statistic here. And if you notice the 4th order statistic, well, if we follow our algorithm, we always look to the left. So we'd be comparing a child left size of 1 to 4 minus 1, which is 3. So we wouldn't have returned the correct node. Well, why do we have to subtract the size of the left subchild? Because all of the nodes that are in the left subchild don't show up when we're looking at our current node 6 over here. So we have to have some way to ignore all the nodes that show up in that left subchild. This is a little bit clearer to show if we're looking for, let's see, how many nodes do we have here? 1, 2, 3, 4, 5, 6. Let's say we're looking for the 7th order statistic. Well, from here, we compare our 5 to 7 minus 1, which is 6. And we need to have some way to ignore all of these nodes after we traverse to the right, because the 10 has no idea how many nodes are to its parents left, how many nodes that the 10 is guaranteed to be bigger than. So we have to subtract the number of nodes over here from the ith order statistic. All right, so finally, let's summarize binary search trees. Why is balancing important? So we talked a lot about the different operations. Why is balancing important? And what is the worst case for a height for a binary tree? Well, a balanced tree means that the tree height stays around big O of log n, and that's important because pretty much all operations, so to answer this question, pretty much all operations depend on the height of the tree. All right, and there are a lot of different types of balanced binary search trees. So trees that have a guarantee on the height. So for example, there's ABL trees, splay trees, B trees, and what we're going to talk about next class period are red-black trees. Or, sorry, next set of videos.